Welcome once again. Today we are going to discuss with liquid chromatography hyphenated with mass spectrometry. We have discussed about liquid chromatography and we have also discussed about the mass spectrometry. Now hyphenation of liquid chromatography with mass spectrometry we are going to deal in this chapter. It requires special devices to hyphenate liquid chromatography with mass spectrometry. These are called as interface systems. So role of types of interfaces and role of interfaces in LCMS that we will discuss. So ionization involving these interfaces may be considered to comprise the following four stages, with the differences between the techniques being associated with the ways in which these stages are carried out. So how they differ, that will be based on how the ionization is taking place. The formation of droplets from HPLC eluate, that is the first step. Then charging of this droplet, desolvation of the droplet, and the fourth is formation of ions from the analyte. So now we will see first interface system, that is thermospray interface used in LCMS. Thermospray may be defined as controlled partial or complete vaporization of liquid as it flows through a heated capillary tube. So schematically, the diagram is shown in this slide. This consists of a heated capillary through which the LC eluate flows, with the temperature of this capillary being carefully controlled to bring about around 95% vaporization of the liquid. The vapor so produced acts as nebulizing gas and aids the breakup of the liquid stream into droplets. The droplets so formed undergoes desolvation as they transverse or traverse a heated region of the interface, and ions are formed from analyte contained in liquid stream by means of ion molecular reaction. So like that of chemical ionization that we discussed in case of mass spectrometry. So altogether we have an heated capillary and a repeller that will divert the flow of molecular ions that are coming in the path of mass spectrometer. So when buffer is present in the mobile phase and analytes are largely ionic in nature or give preform ions in solution, the ion evaporation mechanism is observed. So through when we consider the mobile phases that are used in liquid chromatography, that directs or gives the path for formation of molecular ions. Okay. So that is about the working of thermospray vaporization. So it is going to form the ions or uh, the two required parameters of formation of an low vacuum system and high concentration of mobile phase removal that will be given. After that, it is diverted to the mass spectrometer. Coming to the advantages of interface system, that is thermospray interface system, the interface was much easier to use than the available alternatives that we discussed in case of hyphenation. When we talk about LC coupling with mass spectrometry, the use of a thermospray that was making a very easier and convenient technique. The interface can operate under a wide range of HPLC conditions that are flow rates of 1 ml per minute may be used and mobile phases containing high percentage of water can be accommodated. So the second advantage of a thermospray that lies in wide applicability. The interface can allow unequivocal determination of molecular weight as thermospray spectra usually contains ions simply from molecular species with little fragmentation being observed. So we are going to have this interface system that can deal with the most of the wide determination of molecular weights. The addition of discharge electrode and a filament to the thermospray source widens the range of compounds that may be studied. So these also broaden up the aspect of applicability of thermospray what interface system to the HPLC compounds, determination of compounds by HPLC, and HPLC solvents that may be accommodated. So optimum ionization conditions for a particular compound need to be determined empirically, and it is essential that switching between possible ionization modes may be accomplished easily and quickly. And the fourth advantage lies as what we are going to have, since the simple sample is ionized directly from solution, it is protected from heat and many thermal labile analytes may be studied with little or no degradation. So Thermally labile substances may be studied with the or with the help of thermospray. We can have the analysis carried out for such kind of heat sensitive sample. The sensitivity of interface is compound dependent, but generally high sensitivity is possible by using one of the ionization method available: thermospray, filament, or discharge. So these are some advantages of thermospray interface system. Coming to the disadvantages, if buffer is present in HPLC mobile phase, and this is essential for true thermospray ionization, it should ideally be volatile, and this may necessitate modifying existing HPLC methodology. Whatever methodology employs, they employ most of the inorganic buffers, so they are not volatile in nature. So it requires to modify the method so as to be compatible with the thermospray interface system. The another disadvantage is decomposition of some thermally labile analytes is observed. So they are or temperature sensitive substances. They are getting affected. Such kind of analytes may not be studied. So what we are going to have, the third in disadvantage is the interface is not suitable for high molecular weight. That is, the substances, biomolecules may not be able to get studied with the help of thermospray interface system. Uh, the reproducibility of analytical results is affected by number of experimental parameter, and it's sometimes difficult to control. So reproducibility is the basic need of any kind of detector system, and if MS is going to be the detector, it should have a reproducible result, but that lacks in the case of thermospray interface system, which is going to have the various number of experimental parameter are going to control this reproducibility. So the formation of adducts may confuse the assignment of molecular weight. Many times it has the formation of adducts. The new molecular weight compound is getting formulated at the capillary level when it is heated, and that's why it interferes in the prediction of or assignment of molecular weight to the corresponding sample pick. So usually little structural information is immediately available, and repeller induced fragmentation or MSMS is required to generate this. So wherever we are going with an alone mass spectrometer, it is not possible to identify, but we can couple MS again to give or generate the another spectra of the fragments collected at that subsequent time to have more fragmentation carried out, because fragmentation of all ionic species generated in the interface occurs are often difficult to interpret. So that is the another disadvantage. So we need to couple MS with MS. The interface generates a significant amount of solvent associated chemical noise at low mass, which makes this region unusable for analytical purpose. So solvent associated chemical noise is that what we are going to have the flow rate and the gradient illusion parameter that are going to produce a noise, and which will give the lower concentration sample analyte picks overlapped with it, and that's why they are not getting sensitized. So since the ions generated from the analytes are molecular species, this is not usually a problem, but must be considered when spectra are being interpreted. So at that level, we have to consider this type of noises that are produced due to solvent, what we are going to use in the HPLC. So that are disadvantages of thermospray. We come to the next demand, that is PLEST. That is what we are going to have, the electrospray. High performance liquid chromatography is an effective technique for separation of compounds of high molecular weight. There are, however, two major problems with the use of mass spectrometry for the study of this type of molecule, and these have severely limited the application of Lcms. Especially, these are as follows: the inability to ionize an intact state many of the labile or on or involatile molecule involved. And what we are going to have, the second one, should ionization be possible, the lack of appropriate hardware to allow the mass analysis and efficient detection of the ions of high mass to charge ratio involved. So we come to the another what we are going to have, the uh, PLEST system, interface system, that is electrospray interface. So electrospray is an ionization method that overcomes both of the problems previously mentioned in the previous slide. So a liquid in which the analyte of interest have been dissolved is passed through a capillary at atmospheric pressure and maintained at high voltage. So we are going to have thermospray. We were having heated capillary. We are going to have high voltage, making us feasible conversion of sample droplets into desolvated form of solid molecule. So the liquid stream breaks up with formation of highly charged droplets, which are desolvated as they pass through the atmospheric pressure region of the source towards a counter electrode. So desolvation is assisted by a stream of drying gas. So this is the working of electrospray interface system. So we will see how we are going to have the schematic of electrospray interface system, LCMS interface system. We are going to have a nozzle and skimmer. So the movement of the flow HPLC eluate will take place by this nozzle and skimmer, as it is going to have this heated capillary attached with an high voltage of around 3 to 4 kilovolt uh, voltage supply, and we are going to have a counter electrode which will be placed in front of that HPLC eluate. We are maintaining pressure of around atmospheric pressure of around 2 to 10 torr, and at my mass spectrometer we are having vacuum of around zero point 0.1 to 1 torr. Now whatever the column effluent coming out from HPLC as an eluate will be skimmed by skimmer in form of droplets, and that droplets will be in charge form. So this is the component of electrospray interface system. The mechanism of electrospray interface system, let us talk about it. As described previously, we have discussed about electrospray spectra are produced by passing a liquid stream through a metal capillary maintained at high voltage, that is of around 3 to 4 kilovolt, for the production of positive ions, slightly less and of opposite polarity for the production of negative ions. We are going to have the negative ions that will be produced. This high voltage disperse the liquid stream, forming a mist of highly charged droplets that undergo desolvation during their passage. So as it is going to pass, it is going to get desolvated, and the high voltage is going to give the charge to that droplets. So it will be passed to the source of mass spectrometer. As the size of the droplet produces, a point is reached within 100 microseconds at which the repulsive forces between charges on the surface of droplets are sufficient to overcome the cohesive forces of the surface tension. That is, we call a Coulombic explosion, then occurs and producing a number of smaller droplets with radius approximately 10% of that of the parent droplet. So that is the working mechanism of formation of an charged ions from electrospray. So that is what we are going to have, the mechanism of electrospray. What kind of sample molecules will be utilized for electrospray, that we will discuss in this slide. Ionic compounds that are intrinsically charged in solution that are going to get analyzed with electrospray. Then we have neutral or polar compounds that may be protonated for positive ion mass spectra or deprotonated for negative ion mass spectra under the solution conditions employed. For example, appropriate pH. So that will be the type of sample we can analyze with. We can have a non-polar compound that undergo oxidation, that is with positive ion mass spectra, or reduction, that is with negative ion mass spectra, at electrospray capillary tip. So that these are the type of or variety of sample that can be introduced with an electrospray interface system. All right. So we have discussed about how we are going with an working of electrospray interface system. Now let us talk about how we are going to have the spectrum recorded with electrospray. Electrospray is the softest mass spectrometry ionization technique, and electrospray spectra therefore usually consist of solely or molecular ion. Electrospray is unique, however, in that if the analyte contains more than one site at which protonation in the positive ion mode or deprotonation in the negative ion mode may occur, a number of molecular ions with a range of charge states is usually observed. For low molecular weight material, the number of sites at which protonation can occur is likely to be small, and the electrospray spectrum is likely to be relatively simple and contains only few ions. So as the molecular weight of the analyte increases, particularly of biopolymers or such as proteins are involved, the number of sites at which protonation can occur increases and spectrum becomes more complex in nature. So that is the about typical electrospectra recorded of horse heart myoglobin is shown in this figure, which represents a spectrum. What we are going to have, each of the ions observed arises from attachment of different number of protons and an equivalent number of charges to the intact molecule. So these are the this spectrum, electrospray spectrum of horse heart myoglobin that is shown over here. So this is showing us how we are going to have the representation of the spectra is done. So all this is related with biomolecule study, or how we are going to have the application of electrospray spectrum for large molecular weight compounds in case of electrospray spectrum. Now, how do we interpret the spectrum? Now, when we obtain this such kind of spectra, how to interpret it, that we will discuss in this slide. So for interpreting or for calculating molecular weight of an analyte from electrospray mass spectrum, we are considering here the process that lead to the formation of ions observed. So each ion is formed by the addition of number of species, often protons, to the analyte molecule. So we are having number of protons that are added up with the number of charges residing on that ion being related to number of species added. Obviously, one proton, one charge, two proton, two charge. Like that, we are going to have mass to charge data that will be related. The measured m by z of ion is thus related to the molecular weight of the analyte from which it is generated by the following equation. So for example, if we are having m by z, m is the molecular weight of the analyte and h is the atomic molecular weight of the adduct species. 1 for hydrogen, if we are taking 1, it will be 1 for hydrogen, 18 for ammonium ion. So that will be from where from we are getting that species added up. That is from the buffer solution or the mobile phase that we are going to have the addition taking place. So 23 for sodium, 39 for potassium, etc. That mass will get added up. All right. And n is the number of charges carried by the ion. So this is equal to the number of adduct species if these are singly charged. So obviously ammonium ion, or what we are going to have, sodium ion, potassium ion, they are going to have singly charged. So if they are getting one potassium, one hydrogen, one ammonium, either of it one will get added up. So n will be 1 for that. H will, in place of H, we can write either H, ammonium, sodium, potassium, and write the weight or added up. So M1 will be what is the molecular weight of analyte plus how much will be the number of adducts that are getting added up. Suppose we are getting one hydrogen added up. So 1 into what is the molecular weight of hydrogen is 1. So obviously 1 into 1, that will get added up upon N1. So how much is the number of protons that are added up is the 1. So it will be divided by 1. So which may be rearranged to give M1 N1 is equal to M plus N1 H. And finally, we can have M, capital M, that is the weight where we are going to locate analyte spectra. In case of horse heart myoglobin, we saw the first 600 and up to 1400 the m by z values that were obtained. So obviously what was added up in M line, that will be given by M is equal to M1 N1 minus N1 H. So molecular weight of the analyte will be by subtracting what is the number of adducts that have added up, M1 N1 minus N1 H. That will give us actual weight of the molecular weight of the analyte. So which if the adduct is proton, it will be M1 N1 minus N1, because N1 1 you can write that as the 1 as the subtracted magnitude of proton. So this is how we calculate the molecular weight of the analyte from the electrospray spectrum. Now, what we can obtain structural information from electrospray ionization. In the previous section, we discussed about the generation and processing of molecular weight data from electrospray spectra. The other great strength of mass spectrometry is its ability to generate structural information of the analyte under investigation. So it has already been pointed out that electrospray is the softest ionization process used in MS. So that is transfer of ions to the gas phase is low energy process leading almost exclusively to the production of molecular species. So there are two ways in which structural information can be generated when electrospray ionization is being used. The first, which may be applied to ions generated by any method of ionization, is tandem mass spectroscopy, which was described earlier in the chapter number 3 of mass spectrometry in the section first. So that we have already discussed about how the working of tandem mass spectrometry is taking place. So that can help us to know how we can predict the structure or know the structural information from electrospray ionization. So advantage of electrospray ionization is ionization occurs directly from solution and consequently allows ionic and thermally labile compounds to be studied. In case of thermospray, we were having lack of sensitivity to thermally stable or thermally labile compounds. Only thermally stable compounds were studied. Electrospray applies for both ionic as well as thermally labile species. So we can use inorganic buffers also in that case, in case of electrospray. Mobile phase flow rates from 1 ml per minute, it's 1 ml per minute, to in excess of 1 ml, one what we can consider range of flow rates that can be used with appropriate hardware, thus allowing conventional and microbore columns to be employed. So when we are going to have nanoliter scale to microliter scale, that much flow rates are compatible with this kind of uh, interface system. So these are the very small microbore columns where we can use this interfacing liquid chromatography with mass spectroscopy. Electrospray ionization, in contrast to the majority of other ionization methods employed in mass spectroscopy, produces predominantly multiply charged ions of the intact solute molecule. So this effectively extends the mass range of the mass spectrometer and allows the study of molecular weight well outside its normal range. So unlike that of limitation to lower molecular weight, we are going for higher molecular weight. Just now we have seen one example that was from horse heart myoglobin. So for high molecular weight material, an electrospectrum provides a number of independent molecular weight determination from single spectrum and thus increased precision. So we are going to have a single spectrum which can lead to give us independent molecular weight determination given for in each individual analyte or species in the sample. So that are all advantage making more compatible interfacing of LC with MS by electrospray technique. So now we have some disadvantages of electrospray. Electrospray is not applicable to non-polar or low polarity compounds. So that will be having now when we are forcing the liquid to flow through high voltage, if obviously if it is non-polar, it is not going to show any charge droplets formed, and there will be no further burst of ions that will give us ionization by additive adducts of different charge species on the surface of that droplet. So that will be disadvantage of electrospray. The mass spectrum produced from an analyte in terms of m by z range of the um, ions observed and their relative intensity depends upon a number of factors, and spectra obtained using different experimental conditions may therefore differ considerably in appearance. So we are going to have the considerable dependent what we are going to have the data or spectra which will be corresponding to different intensities. This may or may not have implication on analytical investigations being undertaken. So although the molecular weight information that may be extracted from this spectra, however, is independent of these differences. So whatever we are going to extract, just now we discussed about the structural interpretation, determination of molecular weight. So these individual constituent parameters, analytical investigations, need to be verified further. So separation effects may be observed and the direct analysis of mixture is not always possible. This has potential implication for co-eluting analytes in LCMS. So direct analysis, we can need to have some analysis carried out simultaneously with the another standard added up in the sample. So we are going to have this particular analysis that can lead to have the separation effects shown. Electrospray is an soft ionization method, producing intact molecular species, and structural information is not usually available. So electrospray sources are capable of producing structural information from cone voltage fragmentation, but these spectra are not always easily interpretable. Experimentally, the best solution is to use mass spectrometer capable of MS-MS operation, but this has not consequential financial implications. So a cost increases, and that is the disadvantage of electrospray interface system. Now we come to the another type of interfacing in case of LCMS is atmospheric pressure chemical ionization interface. So atmospheric pressure chemical ionization interface is another of the technique in which stream of liquid emerging from an HPLC column is dispersed into small droplets, in this case by the combination of heat and a nebulizing gas. So as shown in figure 4.21, we are going to have APCI, which shares many common features with ESI, and thermospray, which have been discussed previously. So that can be employed, and that will be the what we are calling it as atmospheric pressure chemical ionization. So as such, APCI shares many common features with electron spray interface and thermospray, which have been discussed previously. So it is a combination of both. We are going to have combination of application of potential along with combination of application of temperature. So we are going to have the differences between the technical methods used for droplet generation, and the mechanism of subsequent ion formation. These differences affect the analytical capabilities, in particular the range of polarity of analyte which may be ionized and the liquid flow rates that may be accommodated. So you can observe in this figure the HPLC eluate that will be taken along with a nebulizing gas stream. So we are going to have the eluate that will be allowed to pass through that controlled heaters, coils that are going to generate the fine droplets with a nebulizing gas, which is forming a dispersed phase of the liquid. All right. So mechanism, we will see about the mechanism of atmospheric pressure chemical ionization. Chemical ionization is an efficient and relatively mild method of ionization which takes place at a relatively high pressure. So when compared to other methods of ionization used in mass spectroscopy, the kinetics of the ion molecular reaction involved would suggest that your ultimate sensitivity should be obtained when ionization takes place at atmospheric pressure. So it is not possible, however, to use the conventional source of electrons, a heated metallic filament, to affect the initial ionization of reagent gas at such precursors, pressures, and alternatives such as nickel 63 or beta emitter or a coronal discharge may be employed. So the coronal discharge is used in commercially available atmospheric pressure chemical ionization system, as it gives greater sensitivity and is less hazardous than the alternative. So we are going to have the discussion stopped over here for about the interfaces used in case of liquid chromatography and mass spectrometry. So we have discussed up till now the interfaces that were related with electrospray, thermospray, and atmospheric pressure chemical ionization. So all these is taken from liquid chromatography, mass spectrometry, an introduction book written by Ardre, 2003. So we are going to have that book, which is recommended for you in your syllabus, that we can use for or here also used for reference. So Robert E. Ardre, with his Ville publication, that is the reference that you have to make. So we will stop here. Thank you.